Okay, we have an interesting integral from the MIT Integration Bee 2019, number 18. We have the integral from 0 to 2, x to the x squared plus 1 times 2 ln x plus 1 dx. To get started with it, the place where I have all the concern really, it's all about this piece right here. The trouble we have is having x in the base and the exponent. That's kind of troubling. And also, it's a little weird having this plus 1. We can definitely break this up and write it as x to the x squared times x. But then here we still don't want x in the base and the exponent. Whenever we have that though, we can always use this trick where we can take, if we have a base of x, we can write it as e ln x. So for this expression here, I can write it as using this e ln x times x squared. And then for this x, we can just distribute this in here. I'm kind of doing that knowing how it turns out, but it is going to work out nicely if we just distribute this in and we get 2 ln x plus x here dx. But the thing I usually want to do with something like this or like this, which is the same thing, I want to know what the derivative is, because it's really making me think that if we take the derivative, it's going to somehow work nicely with all this right here. So when I do this, if I'm going to take the derivative, we might as well try a u substitution on it. So we're setting u equal to x to the x squared, which is the same thing as this, e to the x squared ln x. Then if I take a derivative, first we get back the whole thing when our base is e, but I can write it like this, and we can write it as x to the x squared. And then we need chain rule on this part right here. So first, doing it with product rule, we're going to differentiate the first thing, 2x ln x plus, bring back the first part, x squared, take a derivative of ln x, and we get 1 over x dx. But then I can just clean this up a little bit. We have du equal to x to the x squared. I just want to really clean this part up. So we're going to have 2x ln x, canceling x with x, this just becomes x dx. But then the thing to notice, if we just remember that this is the same thing here as x to the x squared, then what we have for du, that's actually the whole integral, including the dx. So when I do the substitution, everything becomes just du, and all I need to do here is update the bounds. So when we plug 2 in here, then what we're looking at for the upper bound is going to be 2 to the 2 to the 2. For an exponent you want to calculate it from top to bottom, but just notice it doesn't matter here with everything being 2's. But we should do it the right way. So this is the same thing as 2 to the 4, which is just 16. So the upper bound becomes 16. Then evaluating at 0, this part's a little tricky because what's going to happen is we end up with 0 to the 0 squared. Well, 0 squared is just 0. So this is a 0 to the 0 situation. So what happens for our lower bound? It's undefined. Well, that's going to be a problem, as it breaks the whole integral. I can't calculate the lower bound. So we don't want this. Going to get rid of this stuff. You may think this might be leading to one of those 0 to the 0 videos where we have to figure out what this is. Well, I'm not really going that way with it because we don't really care about all that. What's happening here is for our lower bound here, this is the lower bound from the right. We can look at this as 0 plus the positive side of 0, and we can calculate this as a limit. So we don't need all this junk because we've already figured out our integral. We just need to deal with this limit in order to get our lower bound. I mean, obviously we've got a very simple integral. We're just integrating 1. So once we figure out what 0 plus is, we're going to be all set. So to calculate this limit, first what I've done is I've written it in this form here instead of writing it as x to the x squared. Now it's still a problem in this form because if you plug in 0 plus, it's still going to be 0 times minus infinity. So it's still going to be an indeterminate form. But what this is going to allow me to do is then we can just focus on this limit instead. If we can find this limit, we just have e to the base, and we should be able to calculate this. So what I really want is the limit as x goes to 0 plus of just x squared ln x. If I turn this into a fraction, what we can do is use L'Hopital's rule on it. So I can write it as ln x over 1 over x squared, just rearranging it. For L'Hopital's rule, what we want to do is we want to differentiate numerator and denominator. Derivative of ln x is going to be 1 over x. Derivative of 1 over x squared is going to be minus 2 over x cubed. Then flipping this fraction, we're going to end up with x cubed over minus 2x. Cancel an x here. And then what we're left with is this just becomes x squared over, we can write the minus in front, minus x squared over 2. But now evaluating this limit, this is going to be going to 0. So all we need to do, take this 0 value and plug it back in here in the exponent. And so for this limit, this is just going to be going to e to the 0, and e to the 0 is just 1. So what we get for our lower bound over here, this is just going to be 1. And now we're just integrating 1 from 1 to 16. We get u evaluated from 1 to 16. Put this together and it's going to be just 16 minus 1, or 15. Okay, there you go. Good problem today from MIT 2019. Thanks everyone for watching. Have a good day.